All right. I hope you can see my screen right now.
Yes, we can.
Yes,
Yes, we
awesome.
can.
Thank you. So welcome to this first session of two about the hands-on machine learning essentials. My name is David Doppenberg. I'm from the Netherlands. Um, my background is in applied mathematics. I've studied that for 5 years with a specific specialization in research, which is more or less about trying to optimize a lot of processes in general. I'm currently working at Ortec, and yeah, basically the name Ortec already shows you this is also an operations research company, so it's very much in line with my studies. In my day-to-day job, I'm most of the time building a software products, and those products are always focused on either doing optimization with mathematics or machine learning. I'm currently working at Shell and have also been working at Shell for the last 3 years, helping them, yeah, improving their production, but also therefore reducing emissions. In my free time, I love to play board games. I'm playing the piano currently, trying to do a lot of improvisation, which is pretty difficult when you started with just a classical background there. And besides that, I'm trying to go to the gym twice a week, getting my exercise also in there. Um, that's me. Um, t- in the coming 2 days, we will discuss basically a broad selection of machine learning techniques. And today we will really start with the basics. So first of all, because it's really an introductory course, we also start with what is machine learning and more the general topics that needs to be addressed, and such that we have a similar language that we can talk about during the whole course. And then later today, we will start with the first three very basic algorithms, which are linear regression, logistic regression, and k-means clustering. For all of these, we will do intermediate exercises such that we have a nice balance between theory as well as practice. Although the name of this course might suggest that we do only the theory today and maybe tomorrow the practice, I would prefer to do it in stages. Um, because now today you will have, let's say, guided exercises that really tell you what to do. They are really also on a lower level, and tomorrow we will spend our exercise time on one project where you basically have a sandbox and you can do whatever you want with the techniques that we have learned over the 2 days. And so next day we will discuss the model quality and selection, decision trees, and the ensemble methods, and those are, I think, in general, the more used techniques. That's about the program for today and tomorrow. Let's dive into the first bit of theory. Um, for me, it's also the first time in a year that I'm working with this kind of setup for meetings. So I'm please post your messages or your questions in the chat, and I will try to address them on given moments during the course. Um, all right, let's start with the introduction of machine learning. So in this, we were really going to discuss why do we actually need these machine learning methods, give you more or less a general idea of what we mean when we talk about machine learning. Then we will also touch briefly upon uh, when a model is good and not. But those are really early highlights, and the rest of that will be discussed tomorrow during the model selection and quality. So first of all, um, a couple of areas where you can apply machine learning. So those are, for example, face detection. I think nowadays that's a very well-known application of machine learning, where you of course try to, with a computer program, try to detect faces on a video feed or an image. Also very controversial, I think. Um, but besides that, we also have, of course, spam detection or stock trading or whatever. There's basically nowadays you cannot think of. There are basically don't do this. Okay, that's not really nice. I will try to do that in one of the breaks. Um, so, um, but nowadays there are basically endless possibilities where you can apply machine learning and that they are actually also applied in practice. One nice example that I really like, because of course my board game background is the use of AI or machine learning to basically beat the Go game. Um, the Go game is a very difficult and also very complex board game. I think it's way more complex to, for example, chess, because for chess they were already able to solve that in the late 90s, I think. Okay, sorry, my computer is doing a little bit weird. Everything went black. Can you still hear me?
Yes.
Yeah, but I see my screen sharing stopped.
Mm.
All right. A little bit of technical issues at the start. Hopefully that's just the start. You're sharing the screen right now. Can you again see the slide deck?
We can see the slides.
Okay, yeah, thank you. So this was a there's also a very nice documentary about it on Netflix if you want to learn more about it. But basically, they used I think something called reinforcement learning or some a technique very similar to that to come up with the best next action given a certain board state, and they were in the end able to beat the actual world champion in Go, which was at that point in time really not expected because they were not assuming that machines were able to beat the human world champion in the next 5 to 10 years. So that was really, I think, a really interesting case here. So first of all, let's state what machine learning actually is. So machine learning explores the study and construction of algorithms that can learn from and make predictions on data. So why is machine learning so booming over the last maybe 10 to maybe 15 to 20 years? I don't know when it really started, but that's basically when we got big data. Big data basically means data that comes in a really large volume with a lot of variety. So it's not just CSV files, but can also be, let's say, video or whatever kind of format of data. And of course, a lot of different things that is measuring. I think I'm not sure whether I already mentioned volume, but volume is of course one of the more important ones because nowadays we're basically able to track a lot of data in real time, which allows to, of course, more applications. While maybe a decade or 2 decades ago, we were only to do it maybe on given intervals. But besides that, we also have these very powerful machines nowadays. So maybe in the early 90s, it was not even possible to train maybe a on a very large machine. Nowadays, you can actually just on your laptop train any kind of, not any kind of, but a lot of different image recognition neural networks already on your local machine. That, of course, allows to practice more on your own and develop more stuff. And of course, the well-known Moore's law basically saying every so and so years the number of transistors in a computer will double, which makes the computer more powerful. I think nowadays we're already seeing that we are in the decline of this. That because I'm really on a nano scale currently, doubling or creating these machines, and therefore the progress becomes slower. But nonetheless, I think now just a laptop is already so powerful that you can do a lot of machine learning on it, even with large sets of data.
Just one question.
Yeah,
Do you foresee any chip revolution in the future, leading to an exponential increase in computing power?
well, that's very difficult. I'm not a computer scientist, but of course, I think with this current approach, you will get to some certain limit, of course, right? Because we're
Obviously.
now, at some point you're on molecular level, then yeah, at some point it stops. But then there are, of course, also other opportunities that are being developed, like what is it, quantum computers. Still, I'm not really sure how they will be used in practice. But of course, when we have quantum computers on that every person can have one at home, then definitely something will change, right? Yeah. Thank you for your question.
Thank you.
So as I mentioned at the start, machine learning is about prediction, but also learning from your prediction. So basically, those are also two very different questions, I think. So on either side, on the one side, we have the prediction. So we want to know, given our data, given our inputs, what is the response? In this case, we're typically less interested in how we get the response. We just want to know for sure that this response is it can be used in practice. On the other hand, you have something called inference or causality, and that bit of machine learning is the study is really about what's the relationship between my inputs and my output, or in other words, response and the predictor. Those are two very different things, and we will definitely touch that during this course. One important bit in the latter part is that causation, when we want to know more about how we make the prediction, is not the same as correlation. And we always have this very nice classic example. So the recording was temporarily shut down. But of course, there's some correlation between ice cream and sunburn. So you could make a machine learning model based on this, but maybe you already feel this is a kind of a weird model that you use sunburn as input to predict the ice cream sales, because actually there's something called a sun that is actually influencing this whole process. So this is really a typical example of causation versus correlation, because of course sunburn is actually caused by the sun. There, yeah. So of course, if you would just build the model on the sunburn, you're actually not building, the most intuitive or the most logical one. Maybe it works, right? Who tells? But it could work. But of course, in the end, you want to build a model here on the weather, the sun, how hot it will be, how much sun hours we have. That was definitely the one that's going to influence the ice cream sales. So just a very simple but very important example. Never build any kind of machine learning model without knowing what kind of data you have as inputs and how you want to use them, because that can be very dangerous. In practice, for example, I've been creating linear regression models, so to predict, for example, the pressure in a certain condensator. There are, let's say, maybe 2,000 sensors just for that one specific column. Correlation, which I think has been done quite often, you might end up with things that you actually don't want, because maybe in this whole chemical for sure, okay, this ice cream, I shouldn't use sunburn, but when you're talking, for example, about condensator columns, then finding the correct sensors within a pile of 2,000 sensors can be pretty difficult. So what kind of types of machine learning do we actually have? So we for our case, we distinguish between three different kinds. We will only cover two. So so on the broad level, you have supervised learning and unsupervised learning. So sorry, actually, we're going to do them all. You actually have a third type called reinforcement learning. That's the one we're not going to cover in this course, because that's a lot more advanced than the things that we're going to discuss here. So for now, we just have supervised, unsupervised learning. Supervised meaning basically you know the target that you want to learn on. For example, you know your ice cream sales, so you want to predict this. Unsupervised learning, you don't have those target labels that you, and I will show you a better example later on. But within supervised learning, we have two different kinds. We have regression, which is basically we want to predict a continuous response variable, meaning not just a label, so a 1 or a 2, but any kind of number that you can think of. Classification is the bit of machine learning where we deal learning. We have our data points, and they have a certain label, because here we have blue circles and red crosses, and we have apparently two features, let's say x1 and x2, and you can clearly see, okay, this is what we're going to learn on. In unsupervised learning, you don't have these labels. So the idea of this unsupervised learning is that the program finds the way to classify those data points for you. In this case, it ends up with these two clusters. Clustering, for example, can be used for customer segmentation. So if you have a large list of customers that have different behaviors, you might want to cluster them in certain groups because, for example, you want to have a targeted ad campaign to, again, have the most efficient way to promote your product. So the methods we're going to discuss in the coming days are basically almost always a supervised learning algorithm. So you can see, it's a little bit vague maybe, but the bold methods like linear regression, regression trees, logistic regression, and so on are the ones that we're going to cover today, and k-means. One important bit here, so if you start your product, you might want to pick one of these things, is that it's not just, am I using supervised learning or unsupervised learning, but there's always also the question of, do I want to pick an interpretable machine learning technique or a black box one? Again, for example, if you're interested in doing inference, so thinking about causality, why do I get this prediction giving this input? You should never go for the black box, because black box models cannot, or at least can never explicitly say this is 100% the reason why I came to this certain prediction. With the supervised learning ones, you can actually. In the Netherlands, we have these laws that when companies use machine learning, they should actually be able to explain why a certain decision was made, and that can of course be very important for if you want to get a mortgage on your house and you get denied. You want to know, why was I denied this mortgage? If the company cannot explain the reason, then they have a really big problem. But on other cases, there are actually good reasons to use black box models, because you don't care that much about interpretability, but more about performance. So you could think of, if it's about safety, then you want the most efficient and best model. So that really depends on the use case, which of these you're going to pick actually. So now, what is a good model, and when do you consider a model good? I already touched upon this already in the previous slide. So it's basically interpretability versus accuracy, and those actually don't go hand
Hey everyone, I think David is having a connectivity issue, so let's give him a few minutes. Apologies for the same. David, can you hear us?
All right. Sorry about that. My other laptop somehow forced a update. Now joining in again on my other laptop, and I hope my audio is working right now.
Yes.
Yes.
Yeah. So sorry, really sorry about that. Um, from current slide. All right. So I think we were on this slide just talking about interpretability versus the accuracy, and that they typically don't go hand in hand. Basically, increasing interpretability typically means decreasing the accuracy of your model. And of course, but I was already mentioning that really depends on what kind of use case you have. Because if you have something about safety, or if you want to identify a certain disease, then you want to have a very accurate model. But for example, if you want to have a model that classifies if someone should have the mortgage they applied for, yes or no, then it should be a very interpretable model. Of course, there are some ways that if you have a very accurate model, there are, let's say, approximate methods that give you somehow a certain explanation on the prediction, but they will never give you the exact reason why a prediction was made. So yes, this is really depending on the use case, how you make this, how you do the balancing here. So about the data structure of these machine learning problems, you could think of these problems as in a tabular format where you have observations on the rows, and you have certain so that are really the observation moments, and then you have the things that you have measured on the columns. So for example, if we're talking about a sensor, you could think of a certain timestamp as an observation, and then the value of the temperature sensor, for example. Something else, if you have this one is a little bit more difficult if we're talking about a picture, but you could you could see the pixels as inputs and an image as an observation. Then these columns that I was talking about, we have very different names for them across different, let's say, expertises. All these 5 words basically mean the same thing. I will typically refer to these columns as features um, of this observation. If you're more in a statistical background, then you typically would talk about independent variables, or I think typically that's independent variables, but there are also different like explanatory variables or attributes. All those things are the same words for the things that you have measured or the things that are your input. Then similarly for the target variable, so for the thing that you want to predict, the y column in our case, those also have different kind of names. I will typically refer to this as the target variable because it's the target of the model that we're building. But if you're more in engineering background, I think it's typically referred to as a response. Again, in statistics, it will be a dependent variable. Specifically in classification, this will be the label, or more general, just output. But in the end, all these words are the same thing here. This is the thing that we want to predict using the machine learning model. So someone is asking, is this always presented in this tabular format? just thinking. Well, if the techniques that we will be discussing, yes, these are basically always in tabular format. I mean, if we're going to more in-depth things, but that's not part of this course. But I'm not so sure when we're talking about something like a Chat GPT. I'm not sure how the Chat GPT gets its data, but I mean, maybe it will be like a tabular format, but then more dimensions. So this is like really just rows and columns, but then you could have way more dimensions that your data expands to. But yeah, somehow the machine should be able to read the data, and I think it's in some kind of a multidimensional table. I think that's typically that should hold. Again, I've already been referring to big data, but big data in the case of this table basically means we have many columns and also many rows. Basically, more rows than you can fit in your Excel. Just to give you an example, how fast you grow out your Excel. I'm not so good at doing calculations from my head, but basically, if you would have a sensor that generates one data point every second, you will get like 3,600 per hour. But if you start multiplying that with the number of hours in a day and then days in a week, you can already feel like how fast it will actually grow out of these 1.6 million rows that you can load in Excel. So in this case, it's typically really limited. That's also why for machine learning, you don't use Excel, but you refer to more something like Python or other programming languages to do this for you. I think I've been mentioning this already quite a lot. These models, they should always be trained. Training is basically the process of having your historical data and then inputting it to your model, and then the model starts to train on the input that you give. And that how it's doing the training depends, of course, on the algorithm that you pick. If we're talking about a prediction, then of course you have a model that has been trained on the historical data, and then a new observation comes in. But for this observation, we don't have the label or the target variable value. And the idea of the model is that it finds this target value for you. And that one is, of course, called a prediction. Yeah, just to, again, give you a good example of what the difference is between regression and classification. So in this case, we have a data set containing people, and we have certain features. We know certain features about these people. We have the age, the gender, the country, and the height. If we would have a regression problem in this case, we want to, for example, predict the height based on age, gender, and country. Well, if we have a classification problem, in this case, you want, for example, to predict the gender based on the other features. Nowadays, this might not be the best example because predicting gender, I think, should not be the responsibility of a machine learning model. But of course, this is just to give you a feeling what classification means when we talk about a certain data set. Again, we can also use the same data for clustering. In this case, you basically just hand over the whole data set to the algorithm, the model, and then it finds the clusters for you. In this case, it apparently somehow clustered George, Joyce, Jesse, and Jivan, and John and Jack together. If you would look here now, it's probably because of, let's see, John and Jack. Those are the smallest in height, for example. So it might be that this cluster is formed based on height. Or you could also look here at age. So there could be multiple ways why this, yeah, exactly, someone saying they are children. That's very likely the case in here. But you can already see this is a different way of approaching your data. Of course, this, I'm not so sure how familiar you all are with this, but this might sound very simple because you have your data. Someone asking is I'm just going to take a little bit of time to look at the the questions. I think this is a good time just to do a couple of questions. Can we use the words algorithm and model interchangeably, or have they a distinction? No, I think it's more or less the same. No, I think typically you would refer to it as a model. I think the algorithm is more on the internal bit of the model, I would say. So how does it make the prediction, or how is it trained? The model is more, let's say, the abstracted thing that you talk with. So the variables, I think, called features. For now, I'm going to move on with this. So you might think this is a pretty straightforward. I just have my table data. Somehow I have a model and it learns. What's the difficulty in this? The difficulty here is that just training already is not as easy. And that's because of this underfitting and overfitting, or also called bias and variance trade-off. What you see here is basically what we typically do in machine learning is that you have a so-called training set to train your model, and typically you also have something called a test set or a validation set, where you use to validate the trained model. And the important bit here is that the data that you used for validation is not used for training. So basically seeing, it gives you some kind of measure if you predict the validation set on how good your model is, because it now sees data that it has not seen during training. And of course, for this validation set variable, if we're talking about supervised learning. And what you see here in these lines is the error that the model is making in both validation in green and blue for the training. So what you typically see is, and of course here on the horizontal axis, we have model complexity. So if you have a very simple model, what you will of course see is that you're making everything too simple, meaning that you make a lot of mistakes, not only in training, but also in testing. So your model is just too simple. And then you basically end up in this left box, which is called high bias. And high bias basically comes from making everything too simple. So you're basically, you have wrong assumptions, and you should explore more data to see if you can improve your model. On the other hand, what you could do is make your model more complex, more complex, and more complex. Is that the idea of making it more complex for training purposes, at least, is that this error will go to zero, maybe not exactly to zero, but it will decrease. And typically, what will happen to the test set, this validation error, is that it will increase. Basically, what you're doing in the case with a too complex model is that you're training on the errors in your historical data. So if you would think of if you extracted your data from a database, for example, that has been maintained over 30 years by hand, what could have happened over time is that made mistakes because they fill in the data manually. And if you would train your model, of course, on this error, you don't want the model to really pick up on that error. And that's actually what's happening if you make your model too complex, basically saying the model picks up on everything, also on noise, for example, in your training data, which means you test it to find good values.
So, am I right if I say that complexity adds sensitivity? It increases sensitivity.
Yes, I think that's how it works. Yeah. And of course, you don't want to end up in either of these. And that's where the art really is. And how do I actually get in the middle bit here? So how do I get in the middle box where I don't have a high bias, but also don't have a high variance? And that's typically a real task. It's not easy. Just to give you a good example of what overfitting, underfitting, or high bias and high variance mean. Here we have a regression example. So you can, and we want to draw a certain function through it. So here, the most simple function you could think of here is just a straight line. And you could think in this case, yeah, looks pretty okay. On the other hand, if you're going to overfit, what you will see with these functions is that they go through each data point. So even if there's like noise that you measured, their function will basically go through the points. Even if you would increase this degree even higher, then typically these things can go through each point.
So regression is a measure of this in many ways. It's a measure of fit because this is based on the error distance to
Yeah,
the
in this
trend line.
case, yes. Yeah. And of course, in this case, what you want in the end is land somewhere in the middle where you can actually see there's some kind of a seasonal component, which would be ideal. Later, we will discuss how you can actually calculate this kind of stuff. But this is very important to keep in mind and also see it visually what it means to overfit. So this is for regression problems where you want to do continuous target variables. When we're talking about classification, so if you have labels, so you can see we have these red crosses again and these blue circles. Having a very, basically the simplest model is just we have one barrier that in the left side of the barrier you fit crosses and the right side of the barrier you fit circles. So in this case, yeah, of course you make mistakes. I would say in this case it looks already pretty good. But no, okay, it's not so good because you can see here, definitely here in the corner, you miss quite some red crosses. If you're talking about overfitting, then you get these very complex border shapes that basically could draw a border specifically around a certain data point. Yeah, then this is a very clear example where you're making it too complex, and then you get really weird behavior of your model. Again, the appropriate fitting here would be somewhere in between, where you draw this nice smooth curve between everything, and that you just make these two mistakes. And then when you draw this barrier here, it makes perfect sense already that these crosses should actually, maybe they're just mistakes, right? Maybe someone just mislabeled these two data points because they look pretty much like any other circle in this case, given the horizontal and the vertical value of these. All right. So basically the easiest way to prevent overfitting is just having enough data to train on. Unfortunately, that's a lot easier said than done. So in this case, for example, if you would have two regression models, but with different complexity. So the green model, though they're not very well chosen colors. So the green line here is the more simple model, and the red one is again the more complex model. You see these are pretty different. In this case, the green one would be preferred because it again has this nice seasonal trend. And this is the case when you have 15 data points. But suppose you're going to fit the exact same models, but now on, let's say, 100 data points, you actually see that the red and the green are almost overlaying on top of each other. So just introducing more data points will reduce the risk of overfitting because, of course, it becomes more difficult for the model to just overfit on one specific data point. So if you just have more data, that balances out. The unfortunate thing here is that it's not as easy in practice. In one of my projects, I had to train a classifier that determined automatically if a trained regression model should be put into the live environment, that it start making predictions. And the way I got my training data was basically that there were people that using the tool that we built together, and they were going to manually assess each of these models that they trained, identifying whether it was good, yes, whether it was good, okay, or bad. And typically it took around 3 hours to assess one model. Meaning if you would, um, if you want to have more, let's say, an additional 100 data points in your history, it takes about 400 hours to have this. And these people are typically, they're swamped already. They have better things to do, and of course 400 man hours is also just pretty expensive. So it's unfortunately not as easy in practice to just have more data. If you have the option, then of course it's a very good thing to have. Yeah. So another good example here about a misfit I think this was the end of the 90s, maybe the start of the zeros there. The military, of the US wanted to train this classifier to predict based on camera feed whether there was a tank or not standing in front of the camera. So what they did, they made a lot of pictures of in the forest of the tanks, and then of course also just forest. And then what they did, they inserted these photos in their algorithm, trained, tested again. And what they of course nicely did is they had this stack of photos, they put it aside, don't use it for training, set it in a vault, and then also test it. And it worked pretty well. So of course the US, they gave their go, and they started building this for practice. And what actually happened when they were using it is that it was basically just giving random noise. So what happened, and you can maybe already see it in the picture, what happened, the photos of the forest without the tank were made on sunny, no clouds days, and the photos with the tanks were made on cloudy days. And basically the algorithm was in the end just making a prediction on whether it was good weather or not. So just a good example of, it's not just important to do this underfitting, overfitting, but just know, also learn your data and know what you're dealing with, because never train model on nonsense, for example, because garbage in basically always means garbage out, as they like to say. And also a very nice quote here from Albert Einstein is that everything should be made as simple as possible, but not simpler. And I have actually a very nice example of why you should not make it too simple. So here you see two shadows. People, it looks like these people are about to kiss. So basically what you see here is, let's say, you from 3D to 2D, which is basically something called dimensionality reduction. We get rid of the third dimension here and just have these shadows on the plane. But if you again introduce back this third dimension, you see that these two people were just passing by, and not that there was no interaction between these two people. So just a nice picture of showing. Don't make it too simple. Again, up in cases where you have this high bias. And of course, a good tool here to use is just do a data visualization of your data, see if you can already find certain patterns or certain things that stand out. So for example, in this case, if you would have these 8 data points and you would thread a line through it, then you get this decreasing striped line. But if you would actually see the labels of these, so the reds and the blues, that you can actually see that there are basically 2 groups that you should make a model of. Instead of use all data for one model, you might be better in this case to have one model for the blue and one model for the red. So very important always is to have to make pictures, graphs, whatever of your data to just get some understanding. So that's it for this introduction. I don't see any additional questions. So I would recommend, because we're already like 50 minutes underway, is that we take a little break of 5 minutes or something like that. Yeah, I think let's do 5 minutes. And let's be back at 55. And then we will continue with the first machine learning technique, which will be a short one to introduce, and then we will quickly go into some practice. All right, see you in 5 minutes. We will start now with the most simple technique that there is. Already beforehand, I want to say that although it's the simplest, actually it's still a very important one. And I think a lot of companies are still using linear regression. And I would always recommend that if you're doing some kind of let's say a regression exercise for yourself or for your project, always start with linear regression, because it gives you some insights in the basics of your model. Can we actually do this with the most simple model? Because if you can actually just do it with a simple model, then why not? So although I'm going to say it's the simplest model, it will still be a very important model in practice. So again, we have linear regression, which means that we're going to fit a linear model on our data, and a linear model in this case means yeah, let's say in 2 dimensions, we're in this case talking about the straight line through your data points. Of course, when you introduce multiple variables or features, then it's not just, yeah, it's still a straight line, but then in multiple dimensions. So it becomes a little bit more complex to visualize, but still the idea is that there's that it's linear, everything is linear. So in 2Ds, what you can see here is that if we actually don't know what these X and Y features are, labels are, but if we want to predict this Y label with this X feature, then we can actually see our historic data shows already this kind of negative trend, and we can fit a linear line, a linear decreasing line through our data points. Of course, the question here is still, what's the best straight line that we can fit? That's of course the idea of the linear regression model, that there's some kind of a mathematical algorithm that finds this out for you. And the nice thing here is that it doesn't just work with just one X feature to predict one Y feature. You can actually have 2 or whatever kind number of features to predict your Y. And then it looks more something like this. So that you have always this beta 0, which is typically saying where this straight line is intersecting with the Y-axis. And then you have a certain coefficient for one and a certain coefficient for the other feature, which basically say it's pretty straight. It's really intuitive. And if let's say beta is a 0.10, then if um, X grows with 1, then the target variable grows with 0.1. So it's very easy to interpret what all these features are, and that's also why this is explainable model. Basically, you will get the values of these betas, and those will yeah, explain how you got this certain prediction. So if we want to measure the quality of the line that we have a couple of things that we need to discuss. So first of all, we have Y here, just the normal Y in blue, which is the real value. You actually see that here as the blue dots. Then the black Y with the bar above it means the average or the mean of all these Y values. That's typically important for some calculations. And then you have the red Y with the hat on it. It's the Y that you predict. Based on these 3 things, you can calculate the quality of your fit. So one important thing is something called a residual. The residual is actually just the same as the error that you make, and it's a straightforward calculation by just having the actual value of that data point minus the predicted value of that data point. You can again visualize this in your graph, because the error is basically the distance between your red line and the actual data point. If you would sum up n square, so if you would sum up the squared residuals, you get something like the residual sum of squares, which is called RSS. So this is a little bit mathematical, but this symbol basically means you take the sum of everything, and Y with the subscript I basically means the ith observation that you have. And then you need, of course, also need to subtract the corresponding prediction from it. Then you square it and you take the sum of that. You also have something called a total sum of squares, which instead of using this Y with the hat, you actually use the mean. And typically always think about this is that, yeah, you could think of it, just not sure if you should think about it like this, but the total sum of squares you could see as probably the worst fit that you can get. Because what would be the most simple approach if you have a data set and you need to make a prediction of your target variable is just fit the average of all data points. And yeah, I always see this kind of the worst fit, but it's actually called just total sum of squares. And why I say it like this is that because you get some kind of a metric out of it, because what you're going to say, this is the performance of your the RSS is the performance of your model, because this is the sum squared error of your model, which is at the top of this division. And then let's say the performance of the worst model is at the bottom, and then you divide these two. And the lower this thing gets, the better your model. Because in the end, this thing, you want to have as less error as possible. So the actual y value, your predicted y value should be as close as possible to the actual. So this residual sum of square needs to be as small as possible. And then you have this so-called r squared, which is a function, of course, of this residual sum of squares. So making the residual sum of squares as low as possible means that your r squared is as large as possible, because this total sum of squares is always given for a certain data set. You can't do anything about it. It's just a characteristic of your data set. Also, how they typically refer to this is basically explained variance in your data, but that's more technical. So this is one way to estimate the performance of your straight line that you fitted, is using this r squared, and the closer to 1, the better. You can never go beyond 1. So if you have multiple lines, you want to have the one that is close as possible to 1. There's actually a better way to measure the quality of a linear model, and that is using the so-called adjusted r squared metric. Because what you typically see in linear regression is that if you keep on adding variables, so basically we're going towards that overfitting case. If you keep making your model more complex and more complex, the r squared will always increase, because basically you could think of if I make my model, if I add one more feature to my model, it can never perform worse than the previous model, because then otherwise I would just set the coefficient or the beta thing for that specific feature to 0, such that it doesn't have any contribution to the output. So meaning adding variables, adding features to your regression model always improves this r squared metric, or more or less keeps it the same. This is also what you can see here when we have 20 features, it becomes more and more a flat line. But yeah, I think in theory, adding one thing will just always increase your r squared. While this adjusted r squared is actually, you penalize that your model became more complex, but without returning additional performance. And so the formula for adjusted r squared is actually what you can see here. So we added these additional terms, and n here means number of observations in your data set minus 1, and p means the number of features or variables that you have. So suppose you add a feature, but you don't get any additional performance. What actually will happen is that the top of this division, in the end, this complete top, will grow, and then your performance will actually decrease. So with this adjusted r squared, you can actually penalize for too complex models that don't add any additional value. So here you so like 15 or 20 or whatever. If you would look at the adjusted r squared, you can actually see somewhere around 10 is the sweet spot. And you could also see, maybe I don't care about this small bit of improvement, then this one around 7 is already good enough, because with 7 features, you got this bump, and all the other ones are very marginal improvements. So this is how you can actually have a better judgment on your regression models. We're going to discuss about linear regression, and it also leaves us at we're going to start with similar as this. There will be a hands-on machine learning day 1 folder on the GitHub with 3 folders in there. So there will be a linear logistic regression folder and a k-means. And inside here, you will find 2 notebooks, one with the answers. So if you're stuck, you can of course look at this, or later, if you're not able to finish your exercise, just look at the answers. For now, I would prefer that you pick the handout one and start working on that one. And we're going to work on Colab. I hope that you are already familiar from older courses with this. Let me just go there. So I don't know how you are used to, to working with this. Typically, how I do it is I upload my notebook using the option here below file, and then I upload my downloaded. Of course, we're going to do the linear regression one handout. And then there is one more step that you need to take, and that is that below this. So you should upload the data, and the data is also should be on the GitHub. In this case, we're going to use USA_housing.csv. Then you need to upload it here. Basically, what it's doing is that the Python kernel can access the data in this way, and then you can actually see that when I perform these steps, I can load the data. The idea of this exercise is that we have let's say, area statistics of certain neighborhoods. And based on those area statistics, we want to predict the average income of the residents in that city area. So basically get a feeling about some demographic properties of each of these areas, given all the other data that we have here. Important here is that I have put, this will be the first one, which was a pretty straightforward exercise. You will see all those dots, these ellipses. This is the bit where you need to put in some code. So for the first one, it will be a very straightforward, just fill in exercise. You need to fill in these ellipses everywhere. And then that's basically the only thing you need to do. At the end, I have put in a bonus exercise that if you have additional time, then you can play around with the set of features that you use for your model and see if you can improve on it. Let me see, maybe I can just put in the, okay. I think it's, just give me a minute. I need to log in GitHub. This one. It should be in here, but this doesn't look like the main branch. Yeah, the slides, and then in the exercises folder, you find linear regression, the housing CSV, and the 2 Jupyter notebooks for this exercise. And then the idea here is that, let's see, we have until 6. So I think we will probably take half an hour for this. Right. Oh, someone is again asking about the file path. So the idea is that if you upload the notebook using this one, and then you go to this bit here, then there's here upload session storage data, where you can upload your CSV. The idea of this the session storage is that you just upload it for this run. So next time you would refresh, I'm not sure whether it's on a refresh already, but next time you open Colab again, basically this data is erased. So it's just runtime data. Let me just see what happens if I refresh. Okay, well, refresh apparently, yeah, the data is still there, but I think if you really close the whole Colab session, then this data will be removed. So this is, I think, the easiest way to do it. You can also probably have more complex ways that you can have a Google Drive connected to it, but that's probably a little bit too complicated for the setup. It takes too long to accomplish. So please upload the data with the session storage. But I think I will give you around half an hour for the exercises, because then we have 1 hour for the logistic and then 1 hour for the k-means. Yeah, that should be enough. And the idea is that we are going into breakout rooms. Of course, you're free to work on the exercises because you struggle with them. But I will also hop from a breakout room to breakout room and try to help out where needed. I think participants should first be with their Colab. Yeah, so I hope that, I think as a prerequisite for the course, the idea was that everyone followed the Python course. But in the end, Google Colab is a very straightforward one. No. So I'm just checking. I see a lot of questions about the Colab. I hope that you already have a little bit familiarity with notebooks in general, or is this also the first time that someone is seeing a Jupyter notebook? Never worked with this. Okay. So here you can see here I imported pandas as PD. So it's a Python package used for tabular data typically. You can see I am able to use this PD that I defined in this other cell. And that
Sorry,
really,
one question. I
yes.
cannot find this notebook.
Okay, let me just, you were able to access the link that I shared?
It's on GitHub.
Yeah, the link from GitHub, right?
I find that I am on GitHub. I'm on linear regression.
Yeah.
There's US, the exercises, under exercises, linear regression, USA housing. And then you have the answers.
So yeah, there is a handout one and a answer one.
Ah, the handout.
Yeah, the handout one is the one that is used for now.
All right, that's the notebook. All right, fair enough.
Yeah. So also here, what you can see, I define a certain variable called a data frame original, which reads the CSV. I add the variable here, but also in new cells, I'm able to use that variable that I defined there. So the nice thing here is that I can really have a dynamic way of making and experimenting, and that's typically what you want to do with machine learning. You don't want to write one script and run it from top to bottom. Typically, this is really about doing experiments, doing trial and error, getting things working. And that's why notebooks are preferred for this. Oh, I see people have issues with Colab. No, sorry, with GitHub. First of all, let me just finish the introduction with this. So there are two ways to execute a cell in Colab, and that's basically you can press this continue button here or run cell button, which works fine. How I typically do it is I do Shift Enter, and that's doing the same thing. Nice thing about Shift Enter is that I directly move to the one below, which makes executing multiple cells pretty easy. If you want to add a new cell, that's also possible. Let me see where you can do that. I think, oh yeah, right. You have this plus code button. So if you write here, you click this plus code button, you get these new coding cells. So you can do whatever you want. You can type 1 + 1, but you can also define your function yourself and do it like this. So this is a nice way to do it. I think this is basically it on how to use Colab. The one thing, let me just do that one more time because that's the most tricky bit. Because we always need to have the training set, we always need to upload the training set. So what we do is you have a upload to session storage option here. And in this way, you can just for this session in Colab, you can add your data. By the way, you don't need to do it specifically in Colab. If you have a local Python installed with packages already available, then you can of course also do it just locally. The downside there is that it's more of a hassle. You need to install more stuff yourself. Okay. So I hope this was a quick crash course in Colab. I hope that you are able to work with it. So here you can now see this thing is throwing this error because of ellipses, and that's because here you need to fill in the bit of code that selects your feature data, which is actually what we're doing here. So whenever you see these ellipses, that's exactly the fill-in exercise for these notebooks.
I'm having some trouble getting it to find the path to the file, to the CSV.
Okay, right. So what is important is that you actually, with this, you need to see the sample data bit, because otherwise you're probably in the wrong folder. So I don't know where you have uploaded your sample data. So
I copied the path from download folder.
yeah, so that's not possible. So you need to basically, the idea is that you just leave the CSV as the path as is here, and that you
Was
have
it
this,
working?
and then you just have this upload button where you can upload the data, and then everything should basically work. That's the easiest way to get this to work. I'm actually not sure whether Colab is able to connect to your local desktop. I don't think so.
So I should have left it as USA_housing.cv.
Yeah, just leave it as is. Yeah.
It wasn't working though. That's why I
Okay, that's
tried to
weird.
change it.
Yeah.
It's telling me file not found.
Okay. Maybe if we can use your example as a test, then you're probably not able to share the screen. Let me see.
I can try.
Yeah,
I can send the screenshot.
Okay, yeah. If you share the screenshot, that already helps. Yeah, then I can probably.
Give me a minute.
So when someone is asking what outcome are we expecting from this data, there's not specifically any outcome. Yeah, indeed. If you, for example, upload it in the sample data folder, then you should you add the sample data / before the path. And basically, I think it's also possible to upload here, and then you need to add it there. So depending on where you put your data, you need to adjust. Cannot see it after uploading.
I'm sharing it in the chat.
Yeah, please. Can I actually? Why am I not able? Oh, I probably need to download.
I changed it back to how it was.
Yeah, let me see. Downloads, screenshot. Okay.
What's with the error message?
Yeah, okay, I see. But can you also make a screenshot of the basically the bit where you upload the data? So this bit?
All right. Give me a minute.
Yep.
Folder. Sample data.
All right.
No, I don't have. Give me a minute.
Okay, so in the meantime, I'm just going to repeat the process of uploading the data one more time. So, because this should basically work for anyone. So if you have uploaded your notebook, that's the first step you should do. You upload a notebook. Then when
Yes.
it uploads a notebook, it connects a runtime, Python runtime. So that's typically the message that you see first when you press this folder button. And then the step is just press upload to session storage and pick your data set. And then you can see ensure that your file is saved elsewhere. This runtime files will be deleted when the runtime is terminated, which makes sense. And now I have this available. So maybe if someone is not seeing the data immediately, maybe you just need to hit the refresh button or just refresh the whole notebook with this one. But then when you have exactly put data here, so not in the sample data folder and not in the folder above, then the notebook should work out of the back, basically. Everything should work fine.
I'm going to reload.
Okay, I see. Okay,
No.
done. That's good. Let me also download the screenshots from. Oh, no. No.
Sample data.
So exactly, this is what it should look like. Yeah, if you have it like this, then it works as is.
How I can see.
And again, for everyone that has already is able to succeed in all these steps, please just move forward with the exercises, and we will discuss the answers around 45 or 50, something like that.
I'm not saying I clicked on sample data. I'm not saying US housing. I'm seeing California housing test. I'm seeing other CSVs, but I'm not seeing the US housing one.
Okay. I actually think that this is probably just the same data set, but it also should not be in sample data. It should be in the folder above. But
I clicked on the folder above. I'm seeing bin, boots, content,
yeah.
data lab. I think it.
Yeah, if you're in that one, then you are in the wrong one. I don't know. Let me see. How do you actually get back?
David, I think it's content.
Content? Content. Yes. Okay. So if you're in this folder, you should indeed go back to content.
Content.
Yeah. Then there should be.
Content.
You should
Sample
have.
data.
Yeah. So if you do here if you press content, there's these 3 dots. If you do upload, and then you pick the USA_housing CSV, then that should also work. And then let me check if I just restart this.
No, nothing. I'm simply not getting US housing CV. I went on content.
Yeah, but the CSV, you have the CSV, you downloaded the CSV, right?
Yes, I did.
Okay.
And download.
Yeah. Yeah, and then the next step, you try to upload it, right?
Let me try to upload it again. US housing. Okay, I uploaded it.
Okay, and can you see it now?
Yep.
And can you now retry to run the cell?
Will do. No.
Okay, because now I think because I'm in a different folder, for me it works. So if you put data here, so where do you see the data? Is it in sample data or is it in the content one?
Content.
And the other one, did you maybe you can just give the file a new name? Maybe there's like something I cannot see, but if it's in the content, as you can see here, you should be able to load. Just let
me refresh it. Maybe it will.
What you can also do is just if you hit the runtime bit and you say restart session, that basically resets everything.
Let's see. I'm going to do that. No. No, it doesn't work. Sample data. I'm gonna try to copy it as part.
Can you maybe one more time screenshot of both the cell that reads the data as well as the content? So basically,
No, it's, right now it's under sample data.
Okay, but okay, yes. So if you look, I can show you. So if you upload it in sample data, then you need to adjust it slightly, and that makes sense. So let me just show you. Now I also put it in sample data. So if you put it in sample data, you need to do sample_data.
All right, I copied it as a part. Content sample. I copied it as a part.
And now you're able to do it?
Let me see. Yes.
Okay.
All right.
Yeah. All
Thank
right.
you.
Nice. Yeah. So first time we need to figure it out, but then for the rest of the exercises, it will be easier to execute, hopefully. Yeah. Also, given the not so much time. Yeah. So what should we do next if you upload? You just go cell to cell. And then in each cell, there are basically ellipses, and you should fill in the ellipses. So let me show you. For example, this line here, you can see there are ellipses, and there's already a comment that says create X by choosing the required features. So somehow from your data frame that you have loaded, you should extract the features that you want for your model, and you should extract the target and put that in X and Y. That's the first bit here. In the second bit of ellipsis, there's a training and test split that we need to do. So here, somehow you need to fill in 2 arguments of the function. So if you don't know about it, then you can actually look at, hover over the function in GoLab. That's also a nice feature. And it gives you documentation about the function. And for example, here you can see a typical use of train test split. So here you can get some information on how to fill in this method ellipsis. Then here, I think you can do the same thing. So here again, fit, you need to fill in 2 arguments. So you need to fit your linear regression model here. So basically, the exercises should explain themselves. So each cell comes with comments explaining what the idea of this cell is, and then you should just do the exercise that's in there. So sometimes it's filling in with these ellipses, but sometimes it's just inspecting some coefficients that you trained, just to get some insight in what you actually trained. So for this exercise set, we're not going to into breakout rooms, because I think that takes more time to set up for me than it will add value to this session. So hopefully next session we are able to do that. Yeah, so I think someone has uploaded the answer notebook, which is fine, but the answer notebook will have none of the exercises in it, because then the answer notebook contains the cells with all the filled in answers. So it's also fine if you just want to see how it should look like, then you can look at the answers. But there are no particular exercises in there, because everything's already filled in by me. So I see someone's already done. That's good. Also, please, if other people are also already done, then also let me know in the chat, or do a thumbs up of that other message, and I get a feeling of how many people are already done. My idea is to start again in 10 minutes. So at 50, we're going to discuss the answers. Okay, I see there are already quite some people done. Of course, there's a bonus exercise. It's also not a very difficult one, but you can already, if you want, do the bonus exercise of trying to train multiple linear regression models and then pick the one that's best. So that's also an option, or take a short break or whatever.
I'm getting this error in calculating model performance.
Okay, yeah.
Value error, y true and y pred have a different number of outputs. One is not equal to 5.
Right.
I said.
So what you probably need to check, it sounds like the arrays, so the lists that you have are not the same length. So the y that you insert here and the y predicted, they should have exactly the same length. So you should check if you are able to see why that happened.
Yes, should work. But
I see a question about, can you get a similar model performance with less features? How can we find the correlation between features? Right, so that's something that I did not include in the notebook. So basically the idea of the question is that you should just, in this case, do some trial and error. So just remove a feature and see what happens to the performance, or just do it with one feature and see what the performance is. I think if you want to see the correlation, then there should be, let me think. I think there should be a function in pandas. Right. So let me see pandas core. I think if you would use this core method, it calculates the correlation between each and every column. Let me just check that once for you. Let me check. So yeah, so if you do your data frame dot core, which basically is correlation, then you can see you get the correlation matrix of each column with each column. See, because you can see you get these ones on the diagonal. So this gives you some information between the features. Oh. Okay, I'm just going to answer the one question that was posted in the chat, and then we will I will continue just discussing the exercises. So let me just quickly download the screenshot. Right. So again, I think for the person that put it in, so Sophie, It looks like you have put in two different arrays. So you can see you put in one array of length 3,500 and one of 5,000. So I don't know. Let me just do a quick check. So df original dot shape. Oh. Yeah. So I think the 5,000 one is the full. You probably use the full Y, which is this one. And what you should do is, because you made a train and test split here, is use these ones, so the Y test and Y train that you get here, and then make a prediction on your X test and X train, and you should match those predictions. So the prediction of X train should be compared to the prediction, the Y train, and the prediction with X test should be compared to Y test. And I will show you later how, if you're not able to do that, I see it's clear. Cool. I see it's 50. So let's discuss the answers together. So of course, I think in the first two, there is no additional exercise for you. So let me just get rid of this one. So the first thing what you needed to do here, when you needed to select the features, I actually already handed you the list of features that you should use, is that you say, from my full data frame, I only want to pick these features. So for example, if you don't know what this is doing and you don't understand it, the nice thing here is that you can just add a new cell and then execute this cell. And what you can see here clearly now is that you get, again, you get your 5,000 rows, but now you only get 5 columns. That's why, oh, right, because 5 columns, because actually here there are also 5 features. While the original one would have, I think, 6 or 7 even. Same here. In this case, we wanted to predict the average area income. So you should just put in the name of the column. The difference between that you put in the list here is that you're going to get a data frame back. So X is really also a data frame, while Y would be a series. So if you don't understand what the difference is, again, just use the notebook to experiment with it. So you can see here, X is really like in the tabular format, while Y, it's more like, yeah, we call it a Panda series. It also looks very similar, but the series typically just contains one feature. So that was the first exercise. Then the next one is to split your data in a train and test sample. And you needed to fill in the first arguments. So if you would have looked at the documentation, I think the documentation was a very clear example, which is basically almost the same line of code. You say train test split, and the first argument is your X capital, and then the second argument is your Y. You say the test set should be 33% of the data. One important bit I always want to highlight here is that we put in a random state. All these, typically most of these things that you use with scikit-learn is that there's some randomness going on internally. And what you always want to do with these notebooks is that you want to have something that's reproducible. If you don't set a random state, this result will always give you a different split. Although you will always get a 70-30 split, you will get different rows in the splits. Setting this to a certain seed, this is something we call, you also call it a seed. You basically make sure that this function always gives you the same result. And this makes sure that although you do a lot of experiments inside this notebook, you always get the same results, which is of course important, because otherwise next day you wouldn't know why you got the results you got yesterday. So this is not scope of the exercise. So here we want to train our linear regression model. So we just make a empty instance here, and then directly we do a fit. So what you could also have done is do it in 2 lines if you want. This is of course doing the same thing. We first make an empty instance, and then we say fit with, of course, the X and the Y train. And then the nice thing is that because we have a linear regression model, it's really interpretable. And the way you do it is you look at the coefficients. So the coefficients here is basically giving you insight in the price if I have or add one additional unit of price, then this is exactly the amount the target variable will change. Note that you cannot use these to rank your features because the unit of measurement of features can be different. But that's a small side note for people that are a little bit more familiar with linear regression. Also here you can get your intercept, which is the other very important one. And that's basically it with linear regression. And this will be just one number. Then you can make predictions. And you can basically do that using the model.predict method. So if you want to make train predictions, you put in your xtrain. If you want to make test predictions, you put in your xtest. And that's it. And now model quality, this already jumping a little bit ahead with mean absolute error, mean squared error, and root mean squared error. For now, just look at the R squared because that's the only one we discussed. Basically, I gave you an easy method to calculate multiple things in one go. So here you can see when I have when I check the training performance, I get 0.84 R squared, which I think is pretty good. And then when I check the performance on the test, I get a 0.83 R squared. Basically, these are very similar, and that's already gives you some kind of indication in that we're probably not under or overfitting. So let me just do one thing just to show you what could happen. So if I just deselect all these features, I get one feature, and then I need to, of course, re-execute all cells. And we can actually see what happened to the performance of this model when I remove the feature. So you can see this model is really, really, really bad. So basically, if you get an R squared of 0, I think that's typically the worst that you can get, because then this thing is just slightly better than just predicting the average. So this is not good. And you can actually see that's the nice thing with test R squares can go below 0, while training R squares will always between 0 and 1. And then finally, yeah, in this case, this plot will be very different. Yeah, this is a very weird plot. So this gives you already insight. You're basically predicting. Now this almost looks like noise. So this pandas plot.
It's random.
Yeah, it's basically random indeed. So if I just deselect these, or yeah, select them again, I mean, and execute all cells. And then you get this nice line, and then that basically shows you if the actual versus predicted shows this nice line, then this is already a very good model, because apparently now the relationship is now really between the predicted and the actuals are linear. So I think this is a pretty good model. So that's it on the first exercise. So I hope for the people that are already more familiar with Python in general, bear with me, because the first two exercises will be pretty straightforward for you. For the other people, I hope that you see now how this is set up, because basically a machine learning project will always have these kind of steps where you load your data, you select your features and your target, you train a model, and you're going to look at predictions and model quality. So basically all the exercises that we will do, we have this structure, basically these 4 or 5 steps.
I was going to ask you, how do you find R when it comes to machine learning? How good is R to do this stuff? Because I know it has packages and features to do it.
Okay, so I think that's more or less the expertise you are working with. So I think all statistical, if you're more in a statistical working environment, I think everyone is going to use R. I think also the nice thing of R is that I think the university, or how you say it, community of people that are making papers are typically publishing packages there for statistical projects. What I see in general is that if you just go to a random company, and even if they they use machine learning, then they will typically do it in Python. So personally, I think Python in general is more often used and easier to work with than R. But again, that's more or less a preference bit. I know that the community in Python is very large, so you have very well made packages that have a high quality and a high standard. But yeah, I think typically you have more very niche functions that you can use. But for machine learning, I think most of people are just using Python. Are using Python. Okay. I'm going to say let's take a 5-minute break again. And then we will cover everything about logistic regression. Now maybe 5 minutes if it's a little bit long, given everything we still want to cover. Let's do a 2-minute break. Just stretch your legs, and then we continue in 2 minutes. All right, let me open the new slide deck. Oh no, it's the same slide deck. Animations, slideshow. From current slide. Okay. So now we covered the. Oh, just want to bring that. Yeah. Okay. So we covered the linear regression. Now we're going to cover the most. I think that's the most simple exercise for actually. So the technique for classification. So that's a little bit misleading here. Logistic regression is actually not used for regression. you use it for classification. So in the case that we have labels as target variables or discrete target variable. So what we're going to do in this bit of content is that I'm going to try to build up or explain it or introduce this logistic regression in a intuitive way. And that's basically, we start with a simple example where we have one predictor and one response variable. And in this case, we want to predict the gender of a person. So again, the gender is the target. We have, in this case, it's definitely classification because we have labels. So it's a discrete. And we have persons as observations. In this case, we have just one feature, which is height, which is feature. Of course, the most simple way to just look at this is just put all the observations on one line and see how these behave, if we can already observe a pattern. So this is just to give you a feeling of classification in general, because now we have put everything on the line. The most easy next step to make a classification or start doing classification is just add a certain decision boundary. That basically says, oh, sorry. So if we want to, of course, in this case, make a prediction, that means that we get a new person with a height, but we don't know the gender yet. Then the idea here is that we need to find a certain way to deal with that. So that's basically done by doing a decision boundary. And the decision boundary is basically saying I put in somewhere a boundary. Everything on the left is classified as the one label. Everything on the right is classified as the other label. So in this case, we basically put the boundary at 174 or something, and everything on the left will be classified as female, and everything on the right as a male. So in this case, because this new the nice thing is we have already a machine learning method that can do it. So the question now is, could we actually just use linear regression to tackle this problem? We have already established that, of course, linear regression is just for regression, but maybe we can hack our way around it and maybe we can still use it. So because linear regression can only deal with a, let's say, continuous target variable, what we just do is we replace everywhere the m with a 1 and the f with a 0, and then we actually get a numerical target value, although it's still 1 and 0, so it's still discrete. Now we can actually just use linear regression to make predictions. So again, if we make a graph for this, you can now see that we have this separation between 0 and 1, and we can actually just fit a line through it. So if you use linear regression, you can see now we, of course, get some kind of a straight line. In this case, it makes sense that it increases because here there are some m's that are really at the right upper corner. And basically, this model can also make predictions for us. The question now is, how do we interpret this?
If I may, essentially what you're doing is setting a point on that slope and saying anything below it is female or 0. Anything above it is classified as 1.
Yes, exactly. Yeah, that will be indeed the similar thing that we're going to apply here. So typically when we're talking about classification, you look at the results of a classifier in the sense of a probability. Basically saying the probability that this observation is M comes out is the outcome of a certain model. So you can see we have a 0 and 1, then basically everything with a prediction probability of higher than 0.5 will be assigned M. Everything with a prediction probability lower than 0.5 will be assigned F. And this is also a way now to make predictions. Because you can see basically the intersection of this y equals 0.5 and the linear line that we created will be similar to our decision boundary that we saw before. The only downside here is then how do we actually interpret these bits here? Because we just said we talk about these typically, or we can interpret them as prediction probabilities. Because if you're on the line here, m equals 1, then you know for sure the label should be m. If you're on the line 0, you are 100% sure it should be labeled f. But the question now arises, how do we interpret the model predictions that are larger, that are beyond the 1? Because now you actually say, okay, but the estimation is larger, we have more than 1 probability. That's weird, because typically probabilities, they just should be between 0 and 1. So although you can use linear regression, it looks like we should be able to improve a little bit, because we have these weird tail and head of this line that we actually don't want to use and become a little bit weird to interpret. So another way we can do it is just make a histogram, more or less. I think it's called a histogram or a bar chart, stack bar chart of your data. And as you can see here, what we actually display is the percentage. So you have these bins of a certain number of ages, and then you're going to determine what the percentage is of F and M in that certain bin. So you can see, for example, in this bin here, we have around 0.2 Fs and I'm a little bit confused by my own picture. I think it should be 0.2 M and 0.8 F. I think I'm mislabeled the things here. And if I go to the right with the height, you will see that the percentage of M's in my bin will increase. There's a nice thing here that we did not have before with the linear regression. We can now see that this will only go in the y-axis from 0 to 1, which is perfect because that sounds more like actual probabilities. And still we have this 0.5 line that we can use to create our decision boundary, because now whenever there is more than 0.5% inside a certain bin of one category, then we assign that specific label. As you can see here, everything on the left side contains more F labels. So we will assign F. And then everything on the right-hand side, you can see you have more than 50% M labels, so we will assign M. So again, sorry about the mislabeling inside here and inside there. That's a little bit distracting. And one thing that you might observe is that you get kind of an S shape. This is typically what you see in these cases, like S shape. The downside of this approach, of course, is that we need to make these bins manually. Your bins, your graph will change, and your results also. So if you make your bins too small, no data points will fit in. So that's the difficulty with this approach, that the size of these bins in your bar chart, stack bar chart is not easy to find yourself. So again, we should be able to improve. And the improvement here is that we can just find a function that has exactly this S shape, and that we can fit this S shape through our data. And this S shape is called the sigmoid shape. And actually, that's exactly what linear logistic regression is doing. So logistic regression follows the sigmoid function, which looks something like this. So again, if you're interested in the mathematics, that's nice, but for this course, it's not super important that you understand what you see here. Just the most important bit I always want to highlight here is that this function has the properties that we want, basically that it can only go to 0, and so it's always between 0 and 1. How I always do it is basically you check x. So what happens if I increase x to infinity? Then the whole the power bit becomes infinity, and then below you get the same thing. So this thing and this thing both grow similarly fast to infinity. Basically, the limit, and that's a very mathematical story about that, will mean it becomes 1, because you can imagine if this thing grows to infinity and this thing also, then this plus 1 doesn't really matter. So this fraction will go to 1, which is perfect, because then whatever x I can fill in infinity. I never go beyond 1. Now we just want to check that we also never go below 0, and that's just a property of this exponent. And this exponent can just never go below infinity. It can just go very close to 0. So what happens is that you basically get, if you put in minus infinity, you will get almost 0 divided by 1 plus almost 0. And that basically means just 0 divided by 1, which is 0. So whatever you fill in as x, you will always go, you get a result somewhere between 0. So if we want to make a prediction using this function, you just need to fill in the value of your feature. So of course the algorithm will find the beta 0 and beta 1 for you, and then you can just fill in the x and you get a certain prediction probability. But again, it just gives you a certain number. In classification, we're not interested in prediction probabilities as outcome, because we want to know the label actually. And then of course you need to find this decision boundary yourself. So typically you just start with 0.5. But what you can actually do is just tweak this decision boundary to anything you prefer for your case. So in certain cases, it might be beneficial to lower or raise this decision boundary given your context. You need to use this so-called decision boundary to actually get the certain the label that we predict. I see a question here. That is a pretty good question. Can this logistical regression be applied to only maximum of 2 categories? Actually, the form that we see here, yes, you can only apply it to one feature. If you want to do it with multiple features, you labels. Then you say, so you basically have label A, B, and you fit a model that predicts label A and not A, and you're going to make a model that predicts B and not B. And then I don't think you need the third one. I'm a little bit confused here. Maybe you need to create also C and not C, but I think the last one is redundant. So what you basically do is you have multinomial, I think it's called multinomial logistic regression.
This is ANOVA, isn't it?
Yeah, I think so. So you do 1 versus all every time. But I've never used that in practice.
Autonomic.
Yeah, I see indeed dumify it with the last category. Yeah, so I think indeed you don't need the third one. I think you can just have, if you have n categories, you fit n minus 1 logistic regression models. But in those cases, there might be, you can also think about a different classifier, and we will see another classifier tomorrow that can deal, I think, with multiple, that should be able to deal with multiple classes at the same time. But that's a very good question, thank you. So that leaves us now with, again, half an hour for the logistic regression exercises. So in the same folder on the GitHub, you will find a exercise folder called logistic regression, again with a CSV file and a handout and answer file. Again, the handout file will have these ellipses. So let me just upload it file. Now I can just quickly walk you through the idea of this exercise, logistic regression handout. So in this case, okay, yeah, we have a patient data set, and we want to predict whether a person has a higher risk of having a heart disease based on certain measurements. And different libraries in Python for doing machine learning. So this stats models one is nice because it gives you more insight in certain statistics on the model that you trained. So that helps when training the model. The only downside here is that this one doesn't fit an intercept automatically, and that's why I added let's say a feature myself called intercept, which is just a constant one. And this way we can make sure the model actually fits an intercept. Otherwise, that will not be the case. So again, this will look, the way to use these APIs is slightly different, but also again, I just did the ellipses, and you should be able to hover over methods to see how you should use things. Otherwise, you always have the documentation available. So let's take until 45, and then we will take some time to discuss the exercises together, and have again a 5-minute break to, and then we will start the last bit of theory for today. The breakout rooms. So let's see. So no, actually, I'm not going to do that. I think for today, it might be better that we keep everything in one session. If you are all also okay with it, I didn't see a lot of questions last time, so let's do it for now, just in this session, and then post your questions in the chat, or just ask them directly. Please let me know in the chat. Okay. Yeah, then I think it might be a good moment to just go forward, because I also see quite a few participants leave, and I'm not sure whether that's because there's too many time between the exercises, but then I think it might be good to just go over these exercises together, because they shouldn't be, they are not very different than the exercises we did for the linear regression. Of course, I'm already sharing the screen. Cancel. I'm now not sharing the screen anymore. Okay, share screen. Okay. Again, let me upload the answer notebook. And upload the data. All right, so let's look at the exercises. So in this case, nothing changed here. So important here, which is a little bit confusing again, is that we should include, although I said we are just going to include one feature, we also need to include the intercept. So I think it's also possible to just have more than one, cholesterol and the intercept, but for now we just do something simple, one feature and an intercept. So again, we select those as our X, and the target is the target variable. So that one was pretty straightforward. Then the way this API works is slightly different. So in this case, we always need to provide Y and X first. Let me just show you. Yeah, so here you see something called a endogenous response variable and an exogenous variables, which again shows you that in different areas they use different namings for these things. So really the endogenous response variable, so response and dependent variable means target in this case, and exogenous is intercept. Let me just show you where it's not super straightforward from here, but yeah, if you know this thing should be the target variable, then the other ones should be the features, and that's why instead of with the previous scikit-learn we always do x, y, which is kind of confusing. And then we just do the fit, so that's also different. In this case, we need to pass the data directly to the instance rather than the fit method. And this summary bit is actually why I prefer the stats models API in this case slightly more than the scikit-learn one, because we get a lot of statistics or results of our model, which is interesting. So you can see here that the model terminated successfully, which is good. And I think this is already the value that we get, and that we probably will always also see later on, but that's something we can check later. But the rest for now, you can basically skip everything. If you're interested in statistics, then this is interesting for you. Otherwise, it's probably not so interesting. Again, we can look at the values, the coefficients that we fitted. So here you can see this is the coefficient for the cholesterol, and this is the value for the intercept. So more or less we have a value 1 intercept. And now we want to do a prediction. So I use NumPy arrays for this. So I see here a question, why is intercept 1 for all observations? So actually, the funny thing here is that it doesn't really matter what kind of value we put in. The important bit here is except 0, we shouldn't put in 0. The important thing here is that it's a constant thing, because that's actually the whole idea of the intercept. The intercept is something that is constant for all observations. And it doesn't really matter which observation we're talking about. That's just basically, if you would look at the formula, then it should make sense that I can actually pull up the formula. Let me see, logistic. So basically what we say here is we do beta 0. I'm not able, let's enable editing. So I'm doing beta 0 times, sorry, the other way around. So basically you can see it as this. So this feature is like really data, but now I just fill in 1, but 1 times beta 0, it becomes just again beta 0. If you would fill in 2 here, then you will get beta 0 divided by 2. So the idea is that you just fill in 1, such that this the feature here is just the beta 0 here. And this is just the way the API works. So I think if you would use the scikit-learn API, you don't need to provide this intercept 1 column, but that's just the way the stats models API works. But yeah, the whole idea here is that we just add a feature that just has constant value 1, such that in this formula here, it just reduces to beta 0. All right. So what the question here was predict for someone with a cholesterol 50, and basically you do it like this. So you fill in value 50 for cholesterol because that's also the first feature here. And of course, intercept should be just 1. So now you get 0.69. So this person has a what did we say? A more than 50% diameter narrowing. That's what we're going to predict for this feature. Of course, depending on the so we say it's like 70% prediction probability for that specific category. Of course, what we now need to do, okay, first of all, instead of just doing it for one feature, we can also, no, sorry, instead of using just the model, we can also calculate it ourselves, which is basically just the formula that I showed you before, which gives the same value. So you fill in the intercept value. Again, this should be times 1 because that feature we fill in as 1 times the other parameter times the 50 because we picked the 50, and then we calculate the formula, and we get exactly the same value as we had here with the model. And the downside of this is, of course, we just get one prediction. What you can also just do is predict on the whole data set. Note that in this time we don't have test and train sets, just for simplicity. So you just pass the whole X. And of course, you can also calculate this thing again manually by providing X and then just picking the cholesterol column. Again, we assume here that there is a 1 because of the package. Then here we apply our decision boundary to convert the prediction probabilities, because now we can really see if you inspect prediction props. It's like you can see it's an array of values, and if you would check the min, it's 0.30, and if you would check the max, it's 0.64. So all the prediction probabilities in this case are between 0.3 and 0.64. So in this case, we're going to say whenever the prediction probability is larger than 0.5, then we assign label 1, otherwise we assign label 0. So now you can actually see df. We added a column called prediction target at the end, which is the label that we have. Now you can actually see we have a target, so this is the actual one, and the predicted target. So again, we can have a look at how we performed. So this is a pretty straightforward check. So we just do a count of the labels 1 and label 0 and just compare a little bit. So in the actual data set, you see it's more or less balanced. We get almost 50-50% in the labels. But here with the prediction target, we are with the 0.5 decision boundary predicting way more class 1 observations. So the model could be improved. Then maybe it's nice to have a quick look at this. Let me just check what no, I don't think we should cover this. I'm not sure. Did anyone find a better feature to predict, or did everything just go worse? Okay, I see someone put something in. Let me just try that one out. So instead of this one, we're going to use this. And then again, so this is really nice.
Age also gave me a better prediction.
Okay. Yeah, apparently the one that I picked for this exercise was not the best one that we could do. I see. Okay, now it's nice because cool. Yeah. And then see, right, this one is way better. Now you can see here that I think we reduced the number ones from 260 to 185. So that looks a lot closer to the original discrepancy. And yeah, there's something called an accuracy score where that is similar to the, no, it's not similar. It's a way to measure classification problems. So in this case, we also went, I don't know what it was here before, a 55% to a 70%. So this is a nice way to do it. And I think what you could also just do is see So we're now still predicting a little bit too many ones. So maybe we could just do something like this and get something. Oh, that actually, sorry, did I mess up? No, indeed. So you can just increase the decision boundary, and then you can see it affects the number of ones and zeros that we have. I'm a little bit confused. If I put it to 0.6, I would expect exactly more zeros and less ones. So that's basically what happens when you start increasing this decision boundary. You're saying the model, I need to be very, very sure that this is a 1. So you can see it starts increasing the number of zeros that I predict. That's basically how you can use this decision boundary. Tomorrow we will see a more proper way to play around with these prediction probabilities. Cool. Then just check. Yeah, I have no, it's a little bit hard to get a feeling of the energy currently in the group. Do we need a 5-minute break, or is everyone energized to continue with the last bit of theory? Okay, see, I get a mixed one. In that case, I see someone ask for a 5-minute break. I actually also just need a 5-minute break to probably go to the bathroom or something. So, okay, someone needs. So let's just take until the whole hour. I think that's a nice one. Get indeed some coffee. Sounds good. See you in 6 minutes. All right. So we're going to discuss the last bit of theory today, and that will be the clustering technique called k-means clustering. Of course, the clustering method is used for clustering problems, like the one that we saw before, where we don't have any target labels, but the algorithm is going to find those labels, those groups for us. Important here is we don't have a response variable. So the idea of this k-means clustering is that given our data, we're going to partition. I see someone's asking how long it will take. Just to give you a heads up, I think again, theory will be around 20 minutes. And then, yeah, whatever time you want to spend, of course, on the the exercises. But the idea is that we will finish the whole today in an hour. So we're going to partition the n observations that we have into k clusters. And the idea is that we somehow define the clusters that we have, and then each observation will be assigned to a certain cluster based on the distance, the minimum distance to each cluster. So you're basically saying if you have 3 clusters and you calculate for a certain observation the distance to each of these clusters, then you're going to assign it to the nearest cluster. And the objective is to minimize the so-called within cluster sum of squares. And mathematically, that looks something like this. So let me explain what's happening here. There's a lot going on here. But basically, x is our observation. This mu is our cluster. And you see they have different indices. So mu j from the cluster set is actually what this is saying. So basically, if I have 3 clusters, I will have a mu for cluster 1, 2, and 3. Then for each of the clusters, I'm going to calculate the distance from this observation to the cluster and then square that distance. And I'm going to pick the minimum of those clusters because, again, I was assigning that observation to the nearest cluster. So therefore, I will always minimize this bit. And then I will sum all the observations. So I get the distance, the minimum distance to a cluster for each observation, squared, of course, and then sum. And of course, the bit here that I actually need to choose is mu, such that this becomes as small as possible. That is actually what this is saying. So this is very mathematical, but in the end, we will see later with an intuitive example how this is actually working out for us. Right now, because we're going to do the algorithm for a one-dimensional example. So suppose we have these 8 data points, and of course, with clustering, we don't have any target variable, target label. So we don't have labeling, meaning none of these are assigned to a group. So the first step is we need to set the initial so-called centroids, and the centroids is basically the middle point of the cluster for each cluster. And in this case, we're going to set k equal to 3, meaning we're going to use 3 clusters. So in this case, we have an orange, a purple, and a green cluster, and we just put them somewhere randomly. And then based on these centroids, we're going to assign the observations to each cluster. So for the leftmost cluster, we're going to calculate the distance to each centroid, meaning to the orange centroid is this distance, to the purple one is that, to the green one is that distance, and then we need to pick the shortest distance. And now clearly the orange centroid is the closest for the leftmost observation. So we will assign the orange label to this observation. Then what we're going to do is, of course, go to the next observation. So, of course, you can pretty clearly see that the first 3 observations all belong to the first cluster because that's the closest one. Then
I have a question.
Yes.
Does it calculate similarity using means?
What do you mean with similarity?
Like to cluster into group. Does it use it by comparing means and
No. So it's just so you have the centroids which are picked randomly, right? Then
yes.
you have the observation, so you can calculate the distance to the centroid. So basically, the distance from here to there, right? Which is this bit.
Distance from there to a point on the line.
Yes. So yeah, exactly. So this bit is the centroid. So it's basically I don't have any unit of measurement, but it's basically this distance, and then I'm just going to pick the minimum one. Right?
How does it choose? How does it choose where to put that vertical line?
That's random.
It's random.
Yes, it's completely random, and it's not fixed yet. So we will see later on how it's going to refine that vertical line. So right now it's just the 3 are completely guesses basically.
So in a way, it compares the variance, the distance between the variance extremity to the line.
Yeah, kind of. Yeah. It's
Kind
just
of the spread, like the variance.
it's just the distance. So you just calculate basically. Also, if you have more dimensions, it's just like you would measure distance on the map basically. So it's more or less right. It's not 100% what we do, but
No.
it's more or less you just pick the one that's closest.
Thank you.
Yeah. So with the purple centroid, we assigned it to the next 2 observations, because pretty obviously these are closest to that one, and then the remainder 3 are of course closest to the green one. So I think this is nothing really special. But now comes the bit where how this is work. The crux of the algorithm. Right now, what we basically are going to do is we're going to drop the first guesses for the centroids. We're basically going to say just get rid of those, and we now have basically, let's say, a feeling of where this orange group is and where the purple group is and where the green group is. And what we now can do is just calculate the mean of this group and then put the new centroid there. So that's the next step. We drop the centroids and recalculating them by putting them in the middle. You could say, especially for this one-dimensional line, is in the middle, but basically the mean of the group. And now you get your new centroids. But of course, because we have calculated new centroids, maybe there's a new cluster that there are observations that are closer to other clusters. So for example, this green one, you might wonder, this is still, it's not very clear from this picture, but it's not very obvious that the green one is the closest. So what we need to do is basically remove all the labels of the data points and do everything again until it converges. And we will see later what it means that it converges. So again, we're going to calculate for each observation, of course, the distance to each centroid and then pick the minimum. So these first three are closest to the orange. Now apparently these first three, for the second three, I mean, second set of three, those are all purple. So this one changed cluster. And then for the last ones, just the last two that belong to the green one. But of course, because now we have relabeled all the data points, we of course need to recalculate the centroids, because they might have changed again because the mean of the group is different. And then of course, because we changed the centroids, we need to reassign each data point again. But in this case, you can now see nothing changed because the label stayed the same, and therefore also the centroids will be at the same place. And that is the point where this algorithm converged, because the centroids did not move. In this case, it was exactly in the same place, but typically you specify a certain threshold that you say, whenever those things did not move more than a certain threshold, then I converge. So that's basically a simplified version of this. You can also see a 2D example here. So again, we have three classes, and you can see they're a little bit vague, but larger labels, those are the centroids. And every time we recalculate stuff, you can see that the centroids are moving. And therefore also the labels move and the centroids move, and that keeps on going until iteration 14 in this case, and the algorithm terminates with a certain, with the labels that's found. Of course, important here is that the initial pick of your centroids will definitely have impact on the outcome of the model. There's not, let's say, one global best set of centroids. This is typically a multi-solution problem. Therefore, you typically want to maybe set different seeds and then compare. But that's just important to know here. And of course, one thing that we did not discuss yet is now we always pick k equals 3. How should you actually pick k? And this is again has everything to do with underfitting and overfitting. So suppose you pick k as 1. That basically means that all data points will just be assigned to one cluster. The other way around, if you pick k equals n, that actually means that each data point will have its own cluster, more or less. So probably it should be somewhere in between. And again, you can clearly see it here in the pictures. The underfit, you have not enough clusters, and therefore you group things together that should not be grouped together. All the way around, if you have too many clusters, you are not going to group things together that should be grouped together. And of course, the optimal one is somewhere in between. But again, that doesn't really help in how do you actually find the optimal in this case. Again, optimal is difficult because you can never guarantee optimal in this case, but at least you can have some kind of rule of thumb that you can use to find a proper value for k. And the method here is called a elbow method. And what you see here, you can see k is on the x-axis, and the within cluster sum of square is on the y-axis. Of course, the smaller the WCSS metric, the better, the less error you could say. That's not completely true, of course, because there's not really an error in this case. But what you can see here, when you start at k is 1, you get a pretty large within cluster sum of squares. But if you introduce a new cluster, you get a pretty large drop in the metric here, in the KPI. Again, if you introduce 3, so one more, then still pretty large reduction in the WCSS. Then from, I would say, from case 3, yeah, you could argue, yeah, I think case 3, you see this very, yeah, how do you say that, knick, the direction changes, you have this very pointy behavior here, and you could say that's like an elbow. And from here on, when you start adding more clusters, the benefit becomes is smaller and smaller, and probably that means that in this case it's best to use case 3. Of course, this is just one way for the to do this. There's also, okay, yeah, indeed, we pick number 3. There are also other methods that are a little bit out of scope for this course. I think for now it's just good that you know about this and that there are other methods. This is probably the most easy one to deploy. I see a question here: is there an optimal number of features to include for multi-dimension? So again, of course, this is just talking about how to set your algorithm properly. Then again, there's also, of course, the question, how many features should I include? And I don't have a specific tip or whatever for this. I mean, that's just, I think that's how you should check the number of features is probably through data visualization. But what you can also do is check whether there's any actually significant difference between the centroids of those clusters. But yeah, you can see, I think it's more or less data visualization and output analysis that gives you more direction on how you should pick your features. But for now, I actually have never used this method in practice, so I have less experience with how you refine and fine-tune these kind of algorithms. But I would recommend data visualization and post-processing and checking your results, and to get more of a feeling whether all features should actually be included, yes or no. But yes, this is really an experimental thing. You should just also try different things and see how it works out for you. But important is at least that you use this elbow method or another method similarly to get good estimates or a proper choice for your K. And that's basically it for K-means. So again, it's a clustering method. The algorithm is iterative and it is really dependent on the initial choice of the of the centroids. And moreover, you should use something like an elbow plot to avoid underfitting and overfitting of this model. That's it on the K-means. The exercises for this one will probably be a little bit more difficult. But again, let's take until 45 because I feel like you are all pretty fast with the exercises and I don't see a lot of questions. There are a few more pre-processing steps required for this, and let me just walk you through that. Okay, in this case, we get a data set about countries and we get some information about the countries. And the question is, there's basically additional funding available to help out those countries. And the question for you is, which countries deserve this additional money most? And of course, you need to basically give an argumentation based on the data that you have. If you're interested in the more elaborate version of this notebook, you could go to this notebook on Kaggle. And this is basically an adaptation of it. It's a very nice and elaborate, well-made notebook that walks you through how to do K-means clustering. So first of all here, I put in some keyword arguments for you, some default settings that you should use throughout this exercise, so don't really bother about them. Then the most important bit here is that there's some min-max scaling. And why do we actually need min-max scaling? So first of all, min-max scaling basically means that for each feature, it's going to rescale the values, basically by looking at the minimum of the maximum. I'm not so sure what the formula is. Let me just min-max scaling. Right. So you say x minus the minimum of x divided between the distance between the max and the min. And this is basically needed because each feature should have a similar magnitude. And that's because, of course, we are dealing with distances. So if you would have a feature that has magnitudes in the millions, and you're comparing it to a other feature that has only the magnitude in the tens, then it will prioritize the larger one because that will have the largest impact on the distance. Therefore, we need to do this min-mix scaling to have a more proper proper way of to compare features. Then here, what you can see here is basically this bit of code is assigning the default arguments that I set at the top to the k-means clustering. So the only thing you need to care about is the number of clusters that you're going to set. And in the end, there is some bit of code for you that helps you to just read the cluster centers and get a little bit more feeling about what you actually fitted. And then you need to make an elbow plot. And finally, and this is, I think, really interesting, but it's really a bonus exercise. You can actually investigate the clusters that you created and make plots and get more feeling about what are the different clusters, what are the characteristics of the clusters, and those actually give you the most interpretation of the results. But yeah, I think to do. I think the until there everything is more or less similar to what we did before, but this one is pretty is more difficult. Of course, for the elbow plot, I have written down the steps that you need to do. So it has something to do with the for loop, of course, because you're going to create. You need to do it for multiple variants of k, and of course, you need to get for each fitted model that you have the WCSS and then make a plot. Yeah, so please go ahead. Maybe let's take until 50. So you get 23 minutes to work on, 28 minutes to work on this. And again, please let me know if you're finished, because then we can go to the wrapping up of today earlier. So I see a question. Was this the line that you have issues with? Yeah, okay. Yeah, so just to let you know, I made a small mistake here. This bit of code should be updated. Basically, the issue is that df cluster contains a string column. So let me just quickly show you if you just have the time. So I just need 1 minute to show you. The issue here is that there is one, so I can show just, so df cluster. So this country thing has strings and it cannot take the average of the string. So I will update the answer sheet because I just noticed it this morning with this line of code. So basically saying we keep all the columns for call in df cluster dot columns. If column is not country, basically saying keep all columns except the country column, and then it works. I will make sure that this updated notebook will be uploaded to GitHub. So sorry about that mistake. Thanks for pointing out. Yeah, makes sense that you had to look in the answers. I think this one is definitely more difficult. I see also more and more people dropping out. So for the ones that are dropping out, enjoy the rest of your day. But to make sure that most of the people see some answers and we have a discussion about it, it might be best to now discuss the answer sheets together. Otherwise, we will miss that bit, because I think this output, checking the output here, is the most interesting bit, and I think that is also the most complex bit. So let's have a look together. So up to here, yeah, makes sense for everyone that needs to drop. I'm just going to continue. So here, where in this case we don't do any feature selection. Looking online, it was not easy. I couldn't find any Stack Overflow post or something that pointed me to something that's pretty straightforward with these kind of features, whether you should drop or keep all features. So I think this is really the experimentation bit, that you need to be able to explain to yourself why you have all the features, but also do some data analysis to see if all the features are independent enough from each other and actually make sense to keep in there. But unfortunately, there's no easy approach to do feature selection in this case. So in this case, we keep all columns that are numerical, because of course the one with the strings we can't do any clustering on. We need some numerical values, so that's what we do here. We just keep the ones with the features, and we actually don't care about anything else because we don't have a target variable. So here there's a nice describe method that gives you some insight in your data, and you can see, for example, that the income column has a maximum of 125,000, while the total fur, and I need to check what that actually was. Total fur is the number of children that would be born, the fertility, right? So that one has a very different scale. So you can see the minimum is 1.15 and the maximum is 7.5. So that would definitely be an issue if you're dealing with distance-based metrics. So that's why we do, of course, the min-max scaling, but that's already done for you here. Then we start, for example, with the clusters of 3, and then we make a prediction. So you can see the prediction here is that data point 1 will be assigned to cluster 1, data point 2 will be assigned to cluster 2, and here maybe something like data point 7 will be assigned to cluster 0. So when you run this and you do a fit predict, you will get cluster assignment for each observation. And to make it easier for yourself, you can just assign this to a new column called cluster, so that you can easily see in a tabular format which country is assigned to which cluster. And now becomes the interesting bit, because now we want to actually start seeing what the model actually did, because yeah, of course, this is all done automatically for you, but now it becomes interesting. Do the clusters make sense? And can I actually see which cluster is the cluster that needs the most help? Because in the end, that was the question that we wanted to check. So, for example, cluster 1, I think really stands out here, because if we look at the cluster center, so this is the cluster center, so the value of each feature for the cluster, and then at the center. So basically, you can see child mortality is very high for cluster 1, but for the other clusters is definitely lower. Another one that stood out to me, at least, you can look at the income column. You can see, of course, these are the skilled, so the min-max skilled values. So here you can see it only has 0.24, while column 0 has a higher, 0.02, and this income is 36. So you can see that the mean income in cluster 0 is way higher than in cluster 1. Same, of course, but those are kind of correlated features. You can see the GDP is way higher. Also, this one also stands out because the fertility here is way higher. So you can see that at least based on child mortality and income, GDP, I think you would say, maybe also life expectancy, you can see the life expectancy of this cluster is way lower. That probably the countries with cluster 1 need the most attention. Actually, what is nice to see, and that is something I did not include in my case, is that you could also just make a map out of this. And this is actually done in this notebook. So let me just show you this. It's just a nice way to make a visualization. Let me see where that is included in here. At least I thought it was included. Come on, please, please, please. Yes, I can. I mean, in the end, this also gives you a lot of interest because we are dealing with countries. It might be interesting to just have the world map and then color each of the countries based on their cluster. So now you can see, yeah, I don't think the cluster might be really the same, but you can see that the cluster 1, and I think that's also the same cluster that we have as 1, are the most countries. So that makes sense in this case sense. So I think this gives you a way better way to interpret the clusters again and how it did the clustering. So you basically have this darker. This is the cluster 2, are the countries, the more developed countries, and then the yellow one. Yellow ones. The white ones are the ones in between. So again, this is a nice way to visualize your results. Then let's just continue here. Basically, from these numbers, we concluded what we could also see on the world map. And important here, which doesn't tell me a lot, the within cluster sum of squares, but at least the inertia that is populated on the model is the within sum of squares, within clusters sum of squares, sorry. And that is the one that we, of course, need to look at for the elbow method. So what you needed to do for the elbow method was first in a for loop. So in this case, I say I want to investigate K1 until K11. And then in a for loop, I'm going to train my k-means model with the cluster that varies. So the I here is the I in the cluster range that I've set, and then fit, of course, on the same data. And then I'm only interested in the WCSS. So that is the thing I extract from my trade model and store it in this WCSS variable. And of course, I can use this as my y-axis and the cluster range as my x-axis to get the elbow plot. And based on this elbow plot, you probably want to do 3 because then the benefit of having more clusters decreases, and maybe you could argue 4, but based also on the map, the world map, I think 3 is a pretty good option here. And then to the more advanced ones, actually, what's the difference between? Right, so this is instead of just okay. So of course here we looked at really the cluster means, and here I'm going to look at the average of the not minimax scale data, because in the end that helps me a little bit more in understanding what we're talking about. So here you can at least look at again, what are the mean values for each cluster. That gives you more insight. Also, what we can do is here just look at the labels of the cluster. So in this case, we are interested in the countries that belong to a certain cluster. And finally, you can also make graphical representations of the cluster. So what we see here, we can make like a 3D scatter plot because we also add the dimension of colors. In this case, I didn't include a legend, should have done that. But you can see we have 3 different clusters. And now I'm looking at the child mortality, the GDP, and you can clearly see that there is like this almost smooth transition when we look at it. So here on the X value, we look at the child mortality. On the Y value, we look at the GDP. And then the color is the cluster. So here, the countries with low mortality rate, but a high GDP are that, yeah, I think that was cluster 0. I don't know, I cannot recall. But also based on this, and I think that might be an interesting observation, based on this, so just these two features, I have already almost a perfect separation of my 3 groups. So what we could do is rerun this algorithm, but then with just the child mortality and GDP, and then see if we get the similar kind of a grouping. Of course, you can see there are a few that overlap, few data points that are in the other groups, but it's more or less already a pretty clean separation between the data. So I think in this case, you might argue that you don't need to train your model on all the features. You can maybe just do it with 2 or maybe 4, but you probably don't need all of them. I will make sure that this notebook will replace the old notebook. I think one of the pandas functions was updated, and that therefore this function does not deal with the strings automatically. I will make sure that the working notebook loaded probably tomorrow morning. And yeah, I don't see any additional questions here. Also, I agree it might be pretty late for people. If there are no other questions, then I think we can close the session today. Hope to see you all tomorrow, same time. And then we will have more room for your own creativity in the project.